This is Mr. Smith here. Algebra 2. We're looking at section 8.4, part 2. And we just have a few little variants of the things we've been doing yesterday. It's not bad. Remember, we're working our way towards solving rational equations. Now, let me say that differently. We're working our way towards solving equations with fractions. The good news is we already know how to solve equations with fractions, and the method that we're going to use is not going to be different. The only thing that's different now is that we have these nasty things that have variables in the bottom. Okay. To be able to get there, today we're looking at multiplying and dividing rational expressions. Section 8.5 deals with adding and subtracting rational expressions. Think about that. Why does multiplying come before adding? If I'm adding fractions, what do I need? Common denominator. How do you get a common denominator? By multiplying. Okay, so that's the reason we're doing multiplying and dividing today. It's going to lead its way into 8.5, which is adding and subtracting. And if you can do adding, subtracting, multiplying, and dividing, you're now ready to solve an equation in that section 8.6. And then we're done with chapter 8. Okay? So, let us look at this problem. Remember, we're just multiplying two fractions. To be able to do this, we factor everything as best we can. So x minus 4 is already there. The 1 down here doesn't need to be factored. What is the factors for x squared minus x plus 1? How does that factor? The answer is it doesn't. It is already factored. And how would you possibly know that? Other than having the teacher's manual or the teacher himself, you would try all of the possible factors you could think of, and none of them will work. Okay, so that doesn't factor, and you are responsible to know that, which is one of the hardest parts about factoring, knowing when things don't factor. Now, x cubed plus 1. Again, I didn't stress this much in class, but that is a sum of two cubes, and there's a formula or an algorithm that tells us how this factors, and it is x plus 1. It's the same sign. And then it is x squared minus whatever the sign is. It's the opposite sign. And then it's 1 times x plus 1 squared, which is just 1. Okay, and that's the sum of two cubes. You do need to have that memorized. It doesn't have to be out on the front burner, but somewhere on the stove it's got to be there. Okay. And now we look to cancel. And by the way, if you were forgetting, as you were writing this and you were forgetting a little bit, it's very, very probable that these two things should match. So you can kind of use that to help you. Okay, right? These pieces should match because from yesterday we saw that lots of things were canceling out. So this cancels with this. And that leaves us x minus 4 over x plus 1. And we're done. So now we're going to build this idea and take it to division. Right? So how do I divide two fractions? What's the process? Any two fractions, even if they're nice and easy, how do I divide them? Flip which one? Flip the second one, and then what do I do? And then we multiply. Right? So I flip the second and multiply. Or I multiply by the reciprocal. Right, the reciprocal. It just depends on how you learned it, but that's exactly what we do here. 7x, 2x minus 10, times x squared minus 11x plus 30 over x squared minus 6x. Okay. 7x doesn't factor. 2x minus 10, common term factors. To 2 times x minus 5. Up top, we're left with x minus 6, x minus 5. And this bottom one factors by factoring out an x, and that leaves us with an x minus 6. Again, a common term factor. Okay. Now we look for things that cancel. Here I have an x minus 6. Here I have an x minus 6. Here I have an x minus 5. Here I have an x minus 5. And so in the numerator, we get 7x. And what do I get in the denominator? So we got to be careful here of these little floating guys, but that's going to be a 2x. All right. And now the question. Am I allowed to cancel out the x's? All right. Am I allowed to cancel those x's out? And we need to be able to contrast this with something totally different. And so I'm going to put it in red because I don't know why. What if I got this? Am I allowed to cancel out these x's? Okay. When am I allowed to cancel? When am I not? And this is something that a lot of us struggle with. And this is one of the reasons you guys are fraction haters. So the answer is you are allowed to cancel these x's. Look, it's 7 times x divided by 2 divided by x. X divided by x, it's gone. It's just 1. Over here, though, you are not allowed to cancel out the x's. Now, this, again, is not related to this problem. I'm just trying to show a contrast. This, you cannot cancel out the x's, but in this case, we can. What's the difference? You got to see this. This is multiplication and multiplication. And that's the case we have to have to cancel things. It's actually the same reason we're able to cancel all of these things. Why can I cancel x minus x and x minus x? Because everything was being multiplied in both the numerator and the denominator. Okay. You got to have that. All right, so let's look at this again. Again, we're doing division. Now you may say, well, hey Smith, this isn't a fraction. I'll simply put it over 1. Now it's a fraction. How do I divide 2 fractions? Take the second one, I flip it and multiply. So this is 6x squared plus x minus 15 over 4x squared times 1 over 3x squared plus 5x. Okay. And now we have to factor. And I'm like, oh no, this doesn't look like it's going to be very fun to factor. So I'm going to come back and I'm going to save that one to last. So I got 4x squared on the bottom. And I have 1, and this guy looks like it's just common terms factors, so it gives me x and 3x plus 5. Now, seeing on these for an entire day, now you had a practice day yesterday, I know that I have a 3x plus 5 down here, and it would sure be nice if this was one of the things that canceled in the numerator. And I look up at this thing that I'm supposed to be factoring, and I say, well, it almost looks like 3x plus 5 could be one of the factors. And I will tell you, in my experience, and I think you'll find in your experience, probably 9 times out of 10, this guy will be one of the factors of this. So if you're struggling to factor, use this as an idea. No guarantees. No 100% of the times. But more often than not, this will be one of the factors. Now, we still have to come up with the other factor. And we still have to verify that it actually works. So, if 3x plus 5 is one of the factors, what's the other one? How about 2x minus 3? And we should check that. Does that work? All right, so multiply it back out, FOIL it in your head, and it does. It does work. So at this point, 3x plus 5 cancels with 3x plus 5, and we have 2x minus 3 in the top. And what do I get on the bottom? Is it 4x cubed? Yes, it is. Right, 4x squared times x is 4x cubed. And that's our final answer. There's nothing more that we want to do with this. Okay? All right, so why don't you guys give this one a shot on your own. If you're watching the video at home, just pause it. I'll go ahead and take care of the first step because we all know this, right? If I'm dividing 2 fractions, I need to flip the second and multiply. So that's not a big deal. Might as well get that out of the way with. But otherwise, if you would stop the video if you're watching and work on this, when you resume, I'll show you the answer. All right, so hopefully you have the right factors. Hopefully I have the right factors, but I think those are good. And so now we see that the 2x minus 1s, interesting. The 2x minus 1s cancel out. The x minus 2, the x minus 2 cancels out. The x minus 5 cancels out. So what does this thing equal? Is it 9x? Is it 1 over 9x? Or is it 0 over 9x? Or is it something else? So we got to be careful. I mean, and some of you say, well, is it 9x the same as 1 over 9x? No, right? Because, I mean, think about it. If I gave you $90 or I give you 1 over $90, there's a substantial difference. And here, so the 9x is on the bottom. All right, so that piece is good. And what goes in the top? Well, remember, anytime we're multiplying, we can always throw in a coefficient of 1. And so this is just 1 over 9x. There we are. Okay. Again, the primary component of this problem is factoring. All right, so one other idea, and this is a word problem-esque or a real-life situation. So business is always concerned with the idea of efficiency. We want to do things the most efficiently that we possibly can while still getting a good profit, because ultimately we want profits. So in packaging, we have a set volume that we're trying to create, but if we can create it using less surface area, I can save more money, right? Think about a product that gets shipped to you and it's wrapped in plastic. Well, all of that plastic costs money, and if I can take just a small amount of plastic less because I reconfigure the shape to give me the same volume but at a different shape, I can save more money. And companies measure this. Companies measure how much plastic they use to wrap up whatever they're wrapping. If they can use slightly less plastic, they'll do it, because times 1 million widgets or 1 million products a day or a week, it all adds up. So we have this idea of a ratio between surface area to volume, and this is just one measure of a package efficiency or package material efficiency, and we're looking for the smaller ratio. The smaller, the better. Okay, so I'm going to take the surface area divided by the volume, and I'm looking for a small number, and I want to make that number smaller if I can. Okay. So here we go. We have a company that makes flavored popcorn. It puts it in a tin. The tin is a rectangular prism, and the company is designing a new tin that's going to have twice the volume, or twice as the height of the old tin. Twice the height of the old tin, we'll call it that. All right, so they first want us to find the surface area and the volume. So let's find the volume of the small guy. So volume of the small guy. How do you find volume? Length times width times height. So it's S squared H. Volume of the big guy is S squared times 2H. So 2S squared H. And you can see the volumes actually are exactly doubled. Okay. Now we need the surface area. How do you find surface area? What is surface area? It is the area of the surfaces, yes. So we need to find the area of the base, the area of the top. So that should be S squared, but there's two of those, so 2S squared. Plus, sorry, this should be the surface area of the small guy. Surface area of the small guy. Now I need to find the area of this piece. So this is S times H, or SH, and there are 4 of those faces. So plus 4 SH. Okay, if we want to find the surface area of the big guy, it's going to be S squared and S squared, so that's, again, 2S squared. Plus, and now the area of this face is 2SH, and there are 4 of those faces, so plus 8SH. Okay, so this is the volume and the surface area. And now, part 2, we're going to be interested in calculating the ratio of volume to surface area. Let me make sure I have that right. Yeah. So, sorry, surface area to volume. We're going to look at surface area to volume. So we'll call this the ratio for the small guy, and it's going to be surface area to volume. So 2S squared plus 4SH should be the area, surface area of the small, divided divided by the volume, S squared H. And we're going to also talk about the ratio of the big container. And that's going to be equal to 2S squared plus 8SH, all divided by the volume of the big guy, which is 2S squared H. Okay. So part 1, we found the surface area volume. Part 2, we calculated the ratios. Now part 3 wants us to actually compare these numbers. So let me ask you, which ratio is bigger? Or are they the same? So here's the problem. A, there are no numbers there really. B, the numerator here and the numerator here is different. The denominator here and the denominator here is different. So it's really hard to compare fractions. It would be like comparing 2/5 and 5/9. Well, both numerators are different, both denominators are different, so it's really, really hard to be able to make a comparison. So it would be ideal if we had a common denominator. It's really not that hard to get one. So look, this is S squared H. This is 2S squared H. So if I could just get rid of that 2. And I'm going to show this doing a little bit of a unique process. Remember, I can multiply a fraction by the number 1. And it doesn't change it. And for instance, to get rid of this 2, I need to multiply by a half. Half times 2 gets rid of it. But remember, I can't just multiply the bottom by a half unless I multiply the top by a half, so as to not change the problem. And remember, it's the whole top. So what that gives us is S squared plus 4SH all over S squared H. So now I have a common denominator. Now I can compare the two fractions. So the question then becomes, which numerator is smaller? Which numerator is smaller? This numerator on the top, R sub S, or R sub B? Which numerator is smaller? So if I'm looking at this, I see, well, look, this has 4SH, this has 4SH, this has 2S squared, this only has a regular S squared. That means this number, R sub B, has got to be smaller by this factor of 2. All right, so this 2S squared makes R sub S bigger, so R sub B, the bigger tin, actually has more efficiency. Kind of an interesting result. Now, careful here. We need to take this in context. What this efficiency is not saying, it is not saying that this will be cheaper to make. It's not saying that. I mean, this still has more material, and more material costs more money. What it's saying is that this big tin is more efficient volume to surface area to volume than this tin is. Okay, it's just a measure of efficiency. And so usually in a manufacturing setting, we're comparing two things that have the same volume. Okay, I want to ship you this textbook, and so the volume of this textbook isn't going to change. Or I'm going to ship you a glass of water, right? And so the water is a set volume, but the shape for which I send you the volume can change. All right, so usually this is a little bit unique to be talking about two shapes with two different volumes. Also, I'll tell you, I trust that most of you could follow this conversation and this logic, but I would say it's probably a little bit too much of a stretch for most of you to work through that, I would think. This might be on the level of a bonus question for my class, all right, just to give you some sense. So at this point, this concludes part 2 of 8.4. Thanks for your attention. There's a homework assignment, and for those of you in class presently, I'd like you to work on it right away. Thanks. Have a good day.